All right. Hi, everyone. My name is Romuald Cari. I'm a software architect at Devialet, and I'm here to talk today about the Devialet Phantom, which is this product right here, how it was implemented, and how it's a multi-room distributed system. So a few words about Devialet. Devialet is a French company founded in 2007. It started based on a major innovation in the way you amplify audio signals, a way to hybrid digital amplification and analog amplification. We created a bunch of other technologies afterwards, but our very first product was this. It was a very high-end audio amplifier, the Des Premiers, which was received with very raving reviews by audiophile magazines and audiophiles at large. So we worked on extending this amplifier range, basically, and we wanted to make our technologies available to as much people as possible. So we started working on Phantom, and we released a product in 2015. So Devialet Phantom, it's an all-in-one connected speaker. So it's what you would expect from a connected speaker. You can stream music from various online music services. It supports AirPlay, Spotify Connect, stuff like that. So from the very beginning, we wanted to have multiple modes of operations, which are illustrated on the slide here. So basically, you can use it as a single speaker. You just have one in your home, in your living room, for example, or you can pair two and use that as a stereo pair, left, right. But it's also a multi-room solution. So multi-room is basically you have different speakers in different rooms in your home, and you're able to stream music to a specific room or to play music throughout your house in a very synchronized way. So it supports multiple ways of connecting to the network, and that will have some importance later. So we support Wi-Fi, PLC, which is basically networking through your power mains, and Ethernet. So when we started this project, we needed to decide how we would implement that. So we used microservices because all the cool kids were doing it. And so basically, all features in the product are implemented as microservices. So a quick example would be, in this system, you're going to have applications which are responsible for fetching music from the internet, and other applications are going to be in charge of ingesting this music and playing it on the actual device. So you have sources, which are the first ones, and the renderers. So the way we could have made that would have been to make a single application which would have gathered music from the internet and just stream it right out of the sound card on the device. But we wanted to have this separation because if you have a stereo pair, for example, we don't want to have two applications producing audio at the same time and trying to synchronize them. It's much easier to have just one application getting the audio and streaming it to both speakers. So in that case, you'd have one source and two renderers, and each of those things are microservices. So it's really a one-size-fits-all abstraction. It's been really useful for us because, as I was saying, we have different modes of operation. So if you have a source and a renderer on the same machine, which is the case for Phantom, if you play some AirPlay on Phantom, for example, the source and the renderer are going to run on the same physical host. So we can scale this in different ways. We can run both services in the same process, if that's more efficient, if we have resource constraints or things like that. We can run that in two processes on the same machine, or we can run that across a network of Phantoms. So it has further some advantages for us. So we implemented all our applications as lightweight single-threaded daemons. It's really useful because when you work in embedded, you don't necessarily have all the tooling you usually have on desktop. So for example, debugging on an application on a remote target, it's much harder than you'd expect. So if you're doing iPhone development, for example, Apple has packaged this in a really neat way, or Android, you use ADB, stuff like that. But when you're working on your own custom Linux distribution, it's much harder. So debugging remote single-threaded processes is much simpler. Moreover, it's usually just simpler to work mono-threaded code. We also have process isolation, and that's very useful as well. We could have built a single monolithic application running on each device, dealing with every aspect of the device, but any bugs, any hardware issue regarding a subsystem on the product could have caused the whole device to get offline. We'd have to start this application again. So we have process isolation, where basically each feature is hosted by a different process on the machine. That way, for example, if you have a crash of your Bluetooth module on your product, you don't have to take the whole device down. Only the Bluetooth part is going to be down. You can still play music. You can still receive music from another device. And it's also a very flexible design. One example is when we implemented Bluetooth in our product, because initially we didn't have Bluetooth. But when we added Bluetooth, we had to deal with two things. First, we had to get audio from Bluetooth. So we had to get the actual stream that your phone sends to the device. But we also had to deal with remote controls on the Bluetooth, on your Bluetooth phone, or even on our own Bluetooth remote. And so a remote is a service, and the source is another service. And we've been able to combine them in the same process because we had to share this Bluetooth device resource for which only one process can access at a time. And it also allows for very dynamic operations, which is very important for us. In most distributed systems, you usually have a set of requirements on what your what I call topology must be. You need to have at least 3 devices, and you need 2 to keep on moving forward. You need a majority and things like that. In our case, we can just say to our customers, oh, this is a very neat speaker, but you need 3 really to have it work in your house. So we had to work from 1 to many devices. So one aspect of distributed system in the way you interact between your devices. So most systems use a request type based of interactions, where basically it's a model of the web. You have a client which makes a request, the server processes it, and then sends you a response. We need something more because there's a lot of states that we needed to be aware about all around the system. So basically, our notion of a microservice is really a remote object. So a service instance is going to be very similar to an object instance, and an object has methods, but it also has notifications. So an object, a service, can spontaneously send a notification to all its clients saying some state has changed, something has happened, the user pressed play or pause or stuff like that, the volume raised up or went down. This is why we need those notifications. And we also have a property system where each object has basically state, a state that is immediately replicated to all the clients of this service. So as I said, we are doing mostly single-threaded development. So this required us to have an asynchronous API. We don't use blocking calls or anything like that, because anything you would do in that case, if it was on the same machine, you could do a synchronous call, just get the reply from the function you called and just move on with your life. But in our case, the call could be in the same process, in a different process on the same host, or even on the other side of the network. So we needed the API to reflect that. So the API, all our APIs, internal APIs, are asynchronous by default. And we built this framework on Protobuf. So Protobuf is a Google RPC foundation, I'd say. And they have a very neat way of describing services. We made some extensions to add the properties and notifications I talked about. But we derived our own compiler from Google's work. And we use raw TCP sockets as transport because HTTP did not allow us to have those notifications back. WebSockets now we're working on implementing our whole stack on WebSockets in the future. So we call that our RPC layer Call Me Maybe, because when you deal with distributed systems in a home environment, it's really a maybe whether the call is going to go through or not, because users can do crazy things, and many different things can just break your network. An interesting example, we had issues, for example, customers or even us testing at home, we would have problems at some moments in our in using the product. And it would just be because you plugged in a vacuum cleaner or you turned on a lamp or stuff like that. And because we use PLC as a network way of exchanging data between the products, this can cause really important perturbations. You don't have those types, you have problems in data centers, but they're sort of well known. You can have loss of power, loss of connectivity, but in a home environment, really anything can happen, and it's really, really scary sometimes. Another part of working in a distributed environment, as I said, is we don't have DNS, we don't have things like that to find services, and we don't have an infrastructure on which we can rely to say, oh, I'm a service, I'm going to register to that subsystem, and that subsystem will make sure that everybody in the overall system knows I'm here and I exist. So the topology in our case is very dynamic. Our customers can turn on, turn off their product at any time, and we still want them to be able to use their product. So as I said, home networks are really unreliable. So we had to come up with a way to just figure out on the network what's there. So lucky enough, a home network is usually just a single broadcast domain. There's no routing involved between talking between your phone and your speaker or your smart TV or anything like that. It's just one broadcast domain. So we could use a custom UDP broadcast protocol. And then we really split the notion of host discovery from service discovery, because we have a bunch of services running on each device. It can be on some device 50 or more, or it can be just five services, depending on what type of device you may have. So we needed a way to just not pollute the broadcast domain with never-ending broadcast messages in UDP for every single service that would announce itself on the network. So we have host discovery based on UDP, and then we have basically a daemon running on each host, which works as a registrar. So the registrar is in charge of getting the information from local processes, local to this host, that the services exist, what their endpoints are, everything like that. All the required information to announce this service to the world. And a public registry, which is basically the role of this daemon, is to announce to the rest of the world that those services are available on our local host. And one neat thing with that is because each process has to communicate locally with this WhatsApp daemon, if anything happens to one of those processes, it's going to be like a crash, for example. The operating system will do one really neat thing. It's going to close all its connections. And because those connections are closed locally to the host, the other end of the connection, which is the WhatsApp daemon, is going to be notified immediately that the service crashed or was terminated for whatever reason, and can propagate that throughout the network. So a device on the other end of the network doesn't have to wait for a timeout, for example, to figure out that something went wrong with the initial service. And so the final part on our end is, how do you use those microservices, and how basically do you build your application on top of that? So our solution is to use aggregation. So basically any application running on any host, whether it's your phone or an actual device, is going to have an instantaneous view of what the world around it is. And it has to make the best of it. So if everything works perfectly, you just see every services on the network, and you can have a very neat user experience where every feature is available and the user can do anything and everything he wants. But at any time, any of the services can just disappear. So the application has to react to that and adapt itself. So that's what I'm saying with the dynamically adjust the behavior. And one important thing in our system as well is that the state is transient, which I mean, there's really little state that you actually have to save on disk, because it's basically the system is here, two speakers are grouped together, they can play together, but you don't have, I don't know, any data. You don't have to have strict consistency on most of the data that is exchanged in that network. So that's a very neat feature. However, some information is not transient. So typically network configuration, because if the device doesn't even know how to reach the network in the first place, there's no chance it's going to participate in the system. Things like API tokens. If a user logs in into his favorite music service, you don't want to keep his credentials, you just want to have an API token. So this API token has to be stored somewhere and distributed among the different speakers, because each speaker can individually go and play some Deezer or Spotify or whatever. And also one thing which is not transient is the way you configure your speakers. So basically, if the user went through the process of configuring his system and making two speakers part of a stereo pair, he doesn't want, when one speaker goes down or when he unplugs the two and plugs them back in, to have two discrete speakers again and have to do the whole operation all over again. So this is also data which is not transient, and we have to share somehow in the system. So we do have flash storage on each device. It's basically a requirement if we want to store something on a device like network configuration. But we also have issues that you don't have in a typical data center distributed environment. You don't have any reliable source of clock. So the local clocks on the device, we don't have an RTC, a real-time clock, so we don't keep track of the time if the product is not plugged into the mains on the power. We don't necessarily have access to NTP, Network Time Protocol, to synchronize with some time source, because we want the system to be able to work even though it's not connected to the internet. So that's our baseline. We don't have any guarantees on what the topology of the system is going to be. At some point, a user may have 10 speakers in his house, but just decide to have just 2 turn on even one. And in that case, how do you have a consistent write in that system? Because you could write to that device, the device could accept the write, and then it could turn this one off and turn another one on. And this new device has no idea what happened on the previous one. So you don't have any consistency for the user. And for like most people, this is really, there's no way they're going to understand that. It's very bad UX, and it's bad for a product like ours. And also, I said we don't have a requirement on the internet access. So a solution could have been to say, okay, we could create a user account and have some backend service, provide all this information. All the device would have to do is boot up, go to the internet, get its configuration, and move on. But we had a strong requirement not to require internet access. So we had to store some transient state in that system given those constraints. And so how do you do to avoid storage distribution? You just add a new box, and you make sure that this box is required and central to your whole system design. So it's an easy, it was really a quick win and easy solution. And it's not something that we want to use further in the future. You have to understand that when we started this project, it was a very small team. We had very strong time constraints, and we had to figure out how to do things. So we added a box, and this box is the convenient center of everything. So as soon as you have more than one Phantom, this box is required, and it's going to be the place where you store all these states. And the system is not going to be available if this box is not available, and it's by definition a single point of failure. So this is something we are actively working on and making sure that we can provide compromises, I'd say, given our constraints. So this is a place where we store all the non-transient states. But it also has a very useful feature in most domestic environments. By default, there's no PLC networks in your house. Maybe if you use a Freebox, for example, they use PLC, but you can't, as a device, connect to that network. So you have to provide an extra network. And so the dialog does just that. It provides this baseline PLC. It acts as a PLC coordinator, but it also acts as a 2.4 and 5 gigahertz Wi-Fi access point. And it can be useful in some houses where Wi-Fi coverage is not that good, to have this extra box placed in the strategic location to provide support for your Phantom system. And we also had to deal with different constraints. So it's an embedded product, so you may ask, why didn't you use whatever tool is available and everything? So we have constraints, we can guarantee topology, we can do a bunch of things, but we also have very limited resources in terms of CPU and RAM. So a lot of projects are being built using modern technologies, which not always apply to the embedded world. So we strongly prefer development and tools in C and C++, because we know the runtime, it's very predictable, and we also know the tooling and how to debug situations when it's that's especially in the embedded case I talked about. There's also a bunch of licensing issues. You can just use GPL or LGPL code in a product that you ship. It's different from hosting this code on your infrastructure because it never leaves your company, basically, so you're not distributing it. But if you put that code in a product and you sell that product, it's distribution, and you have to deal with all types of legalese, and you have to make, sometimes you even have to open source complete parts of your stack. You can do static linking. You have to run external processes. It's a nightmare. So there weren't really easy to find solutions to address most of our problems. So that's why we had to come up with what I just described. And we learned a lot in the process of building the system. One is design for failure. I guarantee you that failure is going to happen. Error is a normal case in your application. So we made an error in the very beginning, which was to have an error management system based on integers, integer return codes, error codes. And this was from some, I don't know, ideology that exceptions in the C++ runtime are very expensive and too expensive for the embedded environment. That's not really true anymore. In the normal case, you don't pay extra for using exceptions. But in the exceptional case, which is exceptional, you're going to pay a small extra. Use standards as much as possible. So typically, we design a whole UDP discovery system where stuff just existed for it. So Bonjour, for example, or multicast DNS is perfect for discovering hosts on the network. IPv6, we use IPv6 in a new iteration of our system. We don't have to have DHCP and stuff like that to configure hosts. We can just use link local addressing, which comes naturally with as soon as you activate IPv6 on your hosts. In the home environment, multiplex as much as you can on TCP connections. Don't just open a bunch of TCP connections. It's going to be really slow to just get those connections open in the first place. And use UDP for time-critical operations. So the example I had in mind is the user turns the volume on the volume knob on its remote, and it takes an infinite amount of time because it uses TCP, and there's some retries, and the information comes like maybe 10 minutes later. So he's listening to music, and at some point the music just go way up or way down. It's incomprehensible for the user. So just use UDP for that type of things. And the last thing I have to say is that timeout management is really, really hard. It's really not easy to guess and define what a proper timeout value is. It varies from one installation to another. So avoid having to deal with timeouts. And the example I had with the WhatsApp daemon, where you can just be notified that a service was killed, is a way better solution. So I took a little bit more time, but thanks for listening. And if you have any questions, just ask.
We are going a little bit over time, so we will take one or two questions, but then we have to move right on to the next one, okay?
Sorry, guys.
Maybe someone in the middle will catch. Let's see what happens.
Hello, thank you. How do you handle software redundancy? When a server on Amazon goes down, and it goes down to the point where I can't even SSH to it, I just order a new one. And you have customers unplugging the device at the very, very wrong time and stuff like that. How do you handle that?
Basically, it's in the aggregation phase I talked about. So the application which relied on services from that device is basically going to have to adapt. So for example, if you're a source and you were streaming to that device, which was a renderer, You just have to figure out that the renderer is no longer available and just stop trying to send audio to that device and just wait for it to maybe come up at a later time and just reconnect and start streaming to it again.
And how do you rescue that device?
What do you mean?
I mean, if let's say the user unplugs it when you are doing the update, the software update,
Yeah.
it doesn't boot anymore. Do you have some solutions such that Mender or Resin, for example,
No.
stuff like that?
So we use, in our bootloader, basically we have a boot count. If we can manage to boot into the normal Linux for whatever amount of times, we just move into the rescue mode. And in that rescue mode, you have to plug the device to through the Ethernet because you don't have any network configuration. And it's going to try and go fetch the latest update from our servers and just apply it locally. So that's how you rescue a lost dead device.
Yeah, thanks for the talk. I was wondering, how do you, because it's an audio file device, so I guess latency is a big issue.
Sorry.
I guess since it's an audio file device,
Yes.
latency is a big issue.
Yes.
And so with the whole RPC and the containers and the different levels of abstraction, I was wondering how you deal with this.
So latency is really an issue only on the audio path. Like if you have latency in establishing the connection for a renderer to become available to a source, for example, it's just from a user perspective, it's going to be this renderer is not playing for whatever reason, it's booting up, it's trying to connect to the network. But as soon as it's connected and you actually have this link, we're going to start sending audio to it. And the really critical path is this audio path. We have to deliver the audio samples within a limited time frame if we want to stay synchronized with the other devices. So if the audio arrives too late, we just can't play it, and basically the speaker is going to be dead and appear not to be playing. But that's the type of thing that customer support helps our customers debug. Yeah. Thanks a lot, guys.